Hey YouTube, in this video we're going to look at finding all of the zeros of a polynomial equation as well as commenting on the nature of its graphical behavior at zeros where we may have gotten the same answer repeatedly. So let's go and take a look at this first equation here. It says solve the following polynomial equation, then graph the equation and comment on the behavior of the graph at the solution point. So looking at this here, we say setting it equal to 0 first is our first step. And we notice that our y value has already been set equal to 0. So to solve this, primarily we use factoring. I notice that there is a greatest common factor here. So when I factor this here, I get 5 and x as factors of all of our terms. So when we factor that out, I would be left with x squared. Let's see, 5 goes into negative 40, negative 8 times. And we'd say this would be an x. And then over here, let's see, 5 would go into 50 10 times, and then 36. So we have 16. So I'd have 16 here, and we could check that on a calculator. So to factor this completely, we would need to keep factoring this right here. I notice that's a perfect square trinomial. So what I really mean here is I get x minus 4 times x minus 4, x minus 4 times itself. We're going to write this way, but we're also going to write this as 5x times x minus 4 squared equaling 0. So we're going to say that these are the same thing here, okay? And it's important to recognize that because a lot of the time you're going to see it represented this way. And so what we really mean is we get x minus 4 as a repeated factor. So maybe we write a little note here. This is a repeated factor. And the implications of this essentially are that when we go solve this now, because this is factored, now we can say every factor in the product, multiply them together, you get 0. Then we're going to set each one individually equal to 0 and solve it. So I get 5x equals 0, I get x minus 4 equals 0, and I also get x minus 4 equaling 0. So basically, dividing this by 5, I get x is 0. And then adding 4 to both sides of this, I get x equals 4, and I also get x equals 4. So essentially what we've discovered is that this third degree polynomial has 3 solutions here, and these 3 solutions are 0, 4, and 4. And so what I'm going to do is I'm going to list these just twice here, but know that actually, you know what, I'm not. Let's just go ahead and list 4 twice. I think that's a good policy to have here. So what I want you to read down here before we graph this is this. It says repeated solutions in a polynomial graphical behavior. We say when a factor x minus k of f of x is raised to an odd power, or when a factor x minus k of f of x is raised to an even power. What they're really referring to is this kind of notation here, where we say x minus 4 times x minus 4. If we were to write that as x minus 4 to the power of something, we see that it's being raised to an even power. In other words, we got the same answer an even number of times. What would happen if I got the same answer that, like an even number of times versus an odd number of times? So what we're going to do here is we're going to go graph this. So we have 5, negative 40, and 80. Let's go take a look here. So we had 5 x to the third, negative 40 x to the second, plus 80 x. And we see that we have zeros here at 0 and at 4. And in terms of what this looks like, I suppose I could zoom out. You can see that we have this polynomial curve goes increasing, decreasing, and then increasing again. But basically, we have these 2 zeros. But what I want you to notice is that we got 0 for an answer one time. When we did this, 0 was only found as our solution once. Whereas 4 was found twice. So the behavior of a graph at zeros that are repeated, what we'll notice is this. If a 0 occurs an even number of times, our graph touches the x-axis but then turns around. It does not cross the x-axis at that point. And then we'd say that if you get an answer just one time or an odd number of times in general, then our graph does hit the x-axis at that spot, but it also crosses. So what I want everybody to see here is this. We could say that I have a polynomial function, and this polynomial function is x plus 1, so we have a 0 at x minus 1. You can see that here. And we'll do, how about this? We'll do x minus 1, which would give us a 0 at x plus 1. But I'm going to raise that to the power of k. I'm going to let k be a value between 1 and 10, and we're going to go by whole integer values here. So when we go through this, watch what happens to our zeros of this function at negative 1 and 1. Because this one at x minus 1 is going to occur an odd number of times, our graph crosses there. But if I make this even, you'll notice that our graph, it touches at 1, but doesn't cross there. And then we'll go odd. Let me get this out of the way here. We see that it touches and crosses, even. Let me get this out of the way here. Touches, doesn't cross here. Okay, so we can say even, odd, even, odd, even, odd. You can see how it crosses and doesn't cross depending upon even and oddness. So what this says down here, it says repeated solutions in polynomial graph behavior. Essentially, when a factor x minus k happens an odd number of times, okay? So we get this right here, raised to an odd power. We say same solution an odd number of times. If that happens, then the graph of f crosses the x-axis at that x value, x equals k. If it's raised to an even power, we'd say we have the same solutions, or same solution, an even number of times, even number of times. If that happens, then our graph isn't going to cross the x-axis there, which is a useful thing to know when we're graphing things like what we're about to do here. So what we have here is a polynomial function, this fourth degree polynomial function. We want to find all of its zeros and then sketch a graph of the function. So let's start by doing that. Let's find its zero. So we're going to set it equal to 0. And we're going to say, maybe we can solve this by factoring. And I noticed that certainly this does solve by factoring. This, because it's in a trinomial where our leading exponent is a 4 and our middle exponent here is half of that 4, and because we have a constant in the back, we could say this is technically quadratic form. So if I were to rewrite this, let's do this in blue, rewrite this, I could say that this is technically x squared squared minus 18x squared to the first plus 81. And so we're going to factor this just like we would any other polynomial here, except for when we do factor it this time, instead of x, x and x here, we're going to have an x squared and an x squared. So we say, what two factors of 81 also add up to be negative 18? I'd say, well, negative 9 and negative 9. And so the interesting thing here is we get left with a couple of repeating x squareds minus 9, but also at the same time those factor into x plus 3, x minus 3. Conjugate pairs, because they are differences of squares, x minus 3, x plus 3. Let's do it that way. And so I'm going to rearrange this a little bit here, but what I'm going to do is I'm going to rewrite this as x minus 3 squared times x plus 3 squared. And I don't want you to be discouraged by the fact that this is written this way. People think this is ugly. I think this is great because I can tell you right now that if I were to go set x minus 3 equal to 0, of course, without even thinking about it, I say x equals 3 is one of my zeros. And actually, I'm not going to erase that there because when I set x plus 3 equal to 0, I'm going to get x equals negative 3 as another 0. And so if actually I shouldn't even cap that off yet because I'm going to get 3 and negative 3 as zeros like this. And so I notice that I get negative 3 as a 0 twice, and I get positive 3 as a 0 twice, or at least I have these factors raised to powers of 2. So I know that our graph is not going to cross the x-axis at those spots, because they happen an even number of times. So all of this being mentioned here, let's go ahead and do this. Let's put our zeros of our graph on the grid paper here. So we say at negative 3 and at positive 3, our function has zeros. Okay. So in terms of graphing this, we could graph it from the original state here. We say our leading coefficient is 1, which is a positive thing, which means the right side of our graph must end by rising. And then we say our degree here. Our degree being a fourth degree thing means that we have an even degree thing, which means our left-hand side behavior of our graph must be the same as the right-hand side behavior of our graph. So now knowing this, to get the rest of our graph here, we're just going to fill out a table of values. And I'll try to make this kind of blocked off here and give myself some room. We say x, and then we say f of x. And so looking at this here, I would say that we should always plug in 0. That's kind of an always thing. And then I would say let's plug in an x value to the left of and to the right of every 0. So we'd say this right here, we'd say negative 4 and negative 2. Let's say positive 2 and positive 4. And we'll go check these out. So we say plugging in 0. If I plug 0 into this function, I get 81. Instantly, I can tell you I get 81. It's always going to be the constant term. So this one goes up quite a bit. Plugging in the rest of these here, how about we'll start with negative 4. We say f of negative 4. I want you to see this here. We're going to get this. Let me do this. I won't put in this negative 4. I'm going to do some undoing here. We'd say that we get x to the fourth minus 18 x to the second plus 81. And so plugging in now a negative 4, negative 4, negative 4, negative 4. You notice that squaring this and taking this to the fourth power, it's going to make that 4 positive again. So whatever we get for negative 4 here, we're going to get the same thing for positive 4, which is kind of a neat thing. So let's plug this in. We get negative 4 to the fourth. That'd be 16 times 16 is 256. Now we'd say negative 4 to the second is 16. So I'm going to have to check this out here. 18 times 16, 256 plus another 32. Let's see. I'll just do it on here. How about that? 18 times 16. I don't want to make a mistake. So we say 288. So minus 288 plus 81. And then we're just going to check this out here. We get 256 minus 288 plus 81. So we get 49 here when we plug in both negative 9 and positive 9 as a circumstance of just coincidence here. So we say, let's do this here. F of, so we have x to the fourth minus 18x to the second plus 81. This would be a little bit easier this time when we're plugging in, say, let's do a negative 2, which would come out to be the same thing in this case as what we get when we do a positive 2. We would say then I would get 16. Now this is, negative 2 squared is to the 4. Or excuse me, equals positive 4. So 4 times this here would be 40 plus 32 is 72. And then we say plus 81. So I'm going to check this out just so I don't make mistakes on my calculator here. We say 16 minus 72 plus 81. And we say 25. So we say 25 for both of these points right here. So I'm going to go put on our graph these points. I noticed that the highest point here that I got was 81. So how about we do this? We're going to make a little key here. We're going to go 1, 2, 3, 4. And at my fifth spot, I'm going to say that this is 50. I'm just going to make a little note here. And maybe out here at my fifth spot here, I'm going to go 5, just so that my audience knows that that's what I'm going by here. So we say 0, 81. That would be up here at 80, just a little beyond 80. I should put this in red. And we could even label that if we want to. 0, 81. We say 2, 25. So right 2 up about 2.5 units here on the left and on the right, as a matter of fact. Those two right there. And then at negative 4 here, we were at 49, which is just below 50, which would be right about in here. So also at positive 4, we obtain the same y value. So here's the thing about it. Maybe I should go back and color these in blue. We have a graph from left to right that's kind of going through these points right here and has the end behavior that we see on the outside. I hope you can see that this is going to be like a W-like curve. So maybe we start by kind of just getting the middle portion here. We'd say that this would have to curve over and then, come back down. Try to construct this carefully here. Maybe go do 2 points at a time. And then having this end behavior, I know it would have to do something like this on the ends here. And so we could certainly go check this by using a graphing utility, but this graph right here would be the graph of our polynomial function. And it's helpful to know how to find its zeros and know their multiplicity to begin with, or how many times you get them for an answer. Pardon me for using the word multiplicity. I mean to say, getting them an even number of times would imply that our graph is going to touch and not cross, whereas getting them an odd number of times would mean our graph would have crossed at these. Cheers.